Hello students, welcome back. Let's go to section 3 and actually start solving some differential equations. This is our bag of tricks, so to speak. And the proof is postponed until the next lesson. So let's not worry about these. We're going to prove these in chapter 4 along with the more general case, the nth order. For now, let's just use them. Let's begin with the most general case of a second-order homogeneous linear ODE with constant coefficients. And of course, it comes with a characteristic polynomial like this. And the nature of this characteristic polynomial completely determines the solution of the original homogeneous linear ODE, like these. Two real zeros. What does that mean? That means the characteristic polynomial can be factored like this, where lambda 1 and lambda 2 are real numbers and they're different. In that case, we have two linearly independent solutions, blue and red, e to the lambda 1t and e to the lambda 2t, and the linear combination of those two functions will cover entire solution space. How about 1 double zero? In that case, we have just lambda here. In that case, we have e to the lambda t and t times e to the lambda t as the two linearly independent solutions. And of course, the linear combination of those two will cover entire solution space. Now, what if we have two complex zeros like this? The original quadratic polynomial is irreducible. In that case, it is possible to characterize them, rewrite them in complete square plus another square form. In the end, we get a pair of complex roots, alpha plus beta I and alpha minus beta I, which are conjugate of each other. And we can go back to the first case and then write like the first line here, where lambda 1 and lambda 2 are just complex numbers. Or you can go to the second line and use exponential times sine or cosine. Which do you prefer? My preference is the first line. Our textbook author prefers the second. As a matter of fact, I checked many textbooks and almost all the books I checked out preferred the second line. Only a few textbooks in graduate level prefer the first line, and also computer algebra systems, like Mathematica we are working on, prefers the first line. So when I have to do some deep theory, like some significant proofs, in that case I'll use the first line. Otherwise, I'll try to use the second line. Okay, the proof is postponed, but I need something more to compensate a little bit. Are they only linearly independent solutions? No, not really. There can be more, many more, possibly infinitely many more to tell the truth, but it doesn't matter. As long as I have a pair of linearly independent solutions, their linear combination will cover entire solution space actually. And this compensates the other, but then again, this proof is also postponed, so don't worry too much about this one either. So okay, alright, let's talk about how to use these in actual problems. And here are 3 problems. And I believe given time, everybody will see that the characteristic polynomials of these 3 problems corresponds to 2 real zero, 1 double zero, and 2 complex zeros. First, 2 real zero case first. So what is the characteristic polynomial here? 6x squared plus 11s minus 10, isn't it? Coming from the coefficient structure here. And let's factor this. What do you have? 3s minus 2 plus 2, minus 2. 2s plus 5, I think this is right. 3 times 5 is positive 15, minus 4, okay, that's right. And set it equal to 0, and what do we have? S is equal to 2/3, or S is equal to negative 5/2. Did I do this right? So these two are lambda 1 and lambda 2, the characteristic values. And then the solution, the general solution looks like this. It's a linear combination of these two, exponential of 2/3 t from the first, and k2 exponential of negative 5/2 t. It's easy. Coming directly from this and finding lambda 1 and lambda 2, again easy. Let's check. So k1 e to the 2/3 t plus k2 e to the negative 5f t, and then I'll ask Mathematica to simplify this part. 6y double prime, and I need this t in bracket, 11y prime of t minus 10y of t. And of course, I'm going to get 0. That was simple. How about the next problem here? In this case, you're going to get 00. Let's see. Q of s. What is Q of s? S squared plus 4s plus 4, isn't it? And how do you factor it? If you want to do this on your own, stop this playback and do on your own, and then check a little later. They're all easy, as a matter of fact. So you can factor like this. That's equal to 0. Therefore, s is equal to negative 2, 00. So y of t is therefore k1 exponential of negative 2t, which comes from here. And then, what's the other one? E to the exponential of negative 2t, but t times that. So there goes my general solution. Let's check. So this is, let's change to minus 2, here minus 2, and then this is t times. Okay, did I get everything here? And previously, that's 4, and that's plus 4. I copied and pasted this program from the previous problem, and then I'm adjusting. And of course, I'm getting 0. It's hard to say whether I actually ran it or not. Ran it? Yes, it is 0. And of course, if I mistype something like something, then of course I'm not getting 0. Okay, all right. How about the third problem? Again, if you want to work it out, stop this playback and then work it out on your own. Basically, you're working on this quadratic polynomial, so it should not be too much of a problem. 2s squared plus 4s plus 5, and this is quadratic irreducible. You can complete the square like this, squared plus 2s. That's it, isn't it? After factoring those, okay. All right. And then I have to make it a complete square. So plus 1 minus 1, so that this is a complete square. Let's take one additional step. So let's copy and paste all these. And then up to here, this is s plus 1 total quantity squared. And then this minus 1 will come out, so it's minus 2. No, I regret skipping a step. So this is plus 3. So this can be written as, let's say this is s plus 1 total quantity squared. But then again, I want this 2 factored all the way outside. So we get this. Okay, we are ready. K1 is exponential of, let's see, from here, I get minus t, minus 1t. Now cosine, and then not 3/2 t actually, I need beta squared here, so this should be square root of 3/2 t. Not just 3/2 t, I need square root there. So change this to K2 and change this to sine. And that's going to be the general solution that I'm looking for. Shall we check? Is K1 e to the negative t times cosine of square root of 3/2 times t plus K2 exponential of negative t times sine of square root of 3/2 t. And then simplify the left-hand side here. 2y double prime of t plus 4y prime of t plus 5y of t. Am I going to get the right-hand side? Yes, I did. So I did it right. Okay, we went through 3 solutions and they're all straightforward. The last problem may have a bit of computation, but all those computations were in algebra, so no, not really. And if you're unsure about this, or if you just plain do not like this complete square method, then you can always use quadratic formula, and then you can figure those out. Minus b plus minus over here, b squared minus c. b squared minus 4ac, and then I have to divide by 2a, those kind of things. Yeah. Okay, all right. I guess that's it for the standard example problems. And then for higher order, as a matter of fact, I don't know why I assigned these higher order problems here. They fit better for the next notebook. So, okay. We went through the examples, so let's talk about the theory just a little bit. No, I'm not going to go back and prove these. Let's go back to those example problems again. Instead of using our bag of tricks, what if we use Laplace transform method? This is what we have been doing. Q of S is like that, and Y of S is going to be R over Q, where R is degree less than n, so we can decompose by partial fraction like this based upon the factorization of the denominator, and then take the Laplace inversion, we get that. So from here we take one extra step of this decomposition by partial fraction, and then we get the final answer. So taking just one more step, and this one more step is not too difficult as a matter of fact. You don't really have to find out C1 and C2. It's not really a computation intensive step. Just writing as correct form of partial fraction. That's about it. How about this problem? We have complete square, so we have in second line R of S over S plus 1 total quantity squared, and therefore we have S plus 2 and S plus 2 squared form in this decomposition by partial fraction. And that's why we have the justification of this kind of thing. You see, this one generated e to the at directly, but this one, the square thing, needed t times the exponential. Do you see this? This partial fraction yielded this extra t here. Previously, just the first factor and the second factor. I mean the first factor and the second factor. So first fraction, second fraction. Therefore, we have first exponential and the second exponential, and that was it upon taking the Laplace inversion. But here, the decomposition is a little bit trickier because it goes to second power. So we need this t. By the way, that is considered as a justification. How in the world we have this t? There's a connection between the two. Now what about the third solution here? Oh, this is what I wanted. The Laplace transform method, and of course manipulate the characteristic polynomial the way we did here. And then express the denominator is complete square plus another square like this. Square root squared to get this 3/2. And therefore we have cosine sine. That's basically the same thing we did earlier, except that I wrote this extra step, but it's not really adding anything. Overwhelming majority was this kind of completing the square kind of work. And the final line is of course the same. So the Laplace transform method versus our new bag of tricks, basically no difference. Just adding one more line. That's because the Laplace transform method can be considered as the justification of all these. To tell the truth, the proof of all this is related to Laplace transform. That's something we are going to discuss in the next lesson, but here we go anyway. Now, do we have some time for another method, which is a little bit stupid, but okay, let's talk about this thing. Substitution method. This is historically important because originally mathematicians of, 17th century did some differential equations, and then they did it kind of like this. And then it's a historical solution. By taking some educated guess, e to the st power, and then plugging those into the original differential equation. If they do that, and then exponentials stay the same upon taking the derivative, so they will stay all the same, and then we can cancel those out because exponential is never zero. So what do you get? We have an algebraic equation, which is called the characteristic equation. Solve it, and then we have a proof with s value. Only for these s values, we're going to have e to the st because we have to have equal to 0, see? So we get these two solutions, e to the 2/3 t or e to the negative 5/2 t, and then we get a linear combination of the two. You can go back and do these, since this is substitution method. Personally, I don't like it very much, but it's historically important. And some textbooks talk about these kind of things in great detail. But if we have double zero, then that's a bit different story. We have 1. And then how do you get the other is a bit tricky issue. So in order to actually prove it, let's see. Oh yeah, in order to prove it, you actually have to get your hands dirty, plug in everything, and then indeed check it out. I do not recommend it very much. Just use it as they are. Okay, I'm gonna stop here.